Okay, I'm a little bit long. I know I have too many slides, so please be firm and gentle. Understanding uncertainty in a forecast system, as Greg mentioned this morning, that's something we really need to do. So this represents a very major change to us, basically an atmosphere-only ensemble system to a coupled ensemble, coupled ocean, sea ice, and atmosphere ensemble system. That allows, for instance, the Canadian Ice Service to have ensemble predictions or probabilistic predictions out to 30 days that they can use for guidance to their 30-day outlooks. But of course, because it's a major innovation to the system, there's a lot of people that were involved in the production of this, a lot of which went ahead long before I actually arrived on the scene. Okay, so a little bit about the GEPS system, still this very heavy slide here. The GEPS system is a 16-day, 21-member forecast that is now, of course, coupled. Every once a week, it runs a 32-day forecast. I'm going to concentrate on the 16-day forecast. If you looked at the 32-day forecast, it also has an accompanied hindcast with it, and so that would allow you to do some raw, some calibration of the raw forecast, which Arlen Dirksen did in a QGA RMS paper that I encourage you to look at for that. More importantly for the study here, we've got essentially an atmospheric initialization that uses an ensemble Kelvin filter, so it provides basically an ensemble of initial conditions that adequately represent the uncertainty in initialization. However, for the ocean and sea ice, we have a single deterministic initialization or initial analysis that doesn't really have that external or that explicit representation of the uncertainty in the observations or in uncertainty in initial conditions that can then go forward into the forecast. And I'm going to keep on coming back to that. But basically, the ensemble, any ensemble perturbations that we get are all coming from the atmosphere. So as Francois mentioned, one thing that you can is nice to look at in an ensemble system is what is known as the probability of ice. And so again, this is basically just if for a given certain threshold of sea ice concentration, you define whether there's ice or not in a particular grid point. Then if you look over the ensemble, the fraction of ensemble members with ice in it would give you the probability of ice. And of course, 1 minus that probability would give you the probability of no ice in that particular grid part. And so that allows you to do predictions like this animation here, which is from our last Thursday forecast of the probability of ice through most of September and presumably through the sea ice minimum there in September. Going on to the skill metrics I'm going to use here. I'm going to use what is known as the spatial probability score. That is effectively just the spatial integral of the Breyer score. And so that's basically the probability in any grid point that you predict ice minus whether or not you actually observe ice in that grid point, all squared and then integrated over the whole area, or at least the northern hemisphere area in this case. That's very closely related to the integrated ice edge error, which is used for deterministic systems and has been kind of bounced around in a few places in this conference, where essentially you look at the error between essentially the forecasting whether you have ice in the system or not. And again, actually what I'm going to mean in this context is actually the ensemble mean of the integrated ice edge error for each ensemble member. And if I have a deterministic system, as I said, the integrated ice edge error and the spatial probability score are basically equal. But if I have an ensemble system, then I have the fact that essentially the spatial probability score plus the ensemble spread would give me the integrated ice edge error. And so that gives me a way to basically look at the spread in the ensemble spread in my system, or the uncertainty in my ensemble system. So going on to the forecast skill, here's the 15-day forecast skill when validated against its initializing analysis in red, and in blue when I validated against the third party analysis. And most important, and then the black curve there is actually the integrated ice edge error if I compare those two analyses together. And so what you see mostly is that the analysis differences are almost as large as the forecast error, and that's 15 days. If you go I mean, the obvious conclusion for short leads is that as you go to very short leads and you validate against a external analysis, all you really are seeing is differences in the initial conditions. And so I'm going to keep on coming back to that. There's obviously large uncertainty in the initial conditions, and that's going to be very important for an ensemble system. That was my animation that worked, so I don't have to worry about that. Okay, 10-day forecast error, skill comparison between systems. So now I'm going to compare our ensemble prediction system with our deterministic system. That's essentially the blue line to the red line. Yay, the ensemble system does better at probabilistic predictions than the deterministic system. Not a big deal there. Probably more importantly is to kind of look at the comparison with persistence and the deterministic system. Except for May and June, which occurs twice in that graph, the deterministic system is outperforming persistence. So that's good. Obviously, when we have large when persistence doesn't do very good during the summer melt season, unfortunately, our dynamical model isn't doing much better. But on the other hand, in the November freeze period, you can see that, again, where persistence doesn't do good, our dynamical model is doing considerably better. And then in the, essentially in the maximums and minimums, where again, persistence now does very well, at least for the September minimum, the dynamical systems are greatly improving on persistence. And for the March maximum, well, maybe the deterministic system isn't improving it that much, but in terms of probabilistic predictions, the ensemble system is doing a pretty good job. Now, if we add, again, the analysis error into that mix, you can see that the forecast error is very much related to the initialization uncertainty. And so where you have large uncertainty in the initialization conditions, you have large forecast error. And so, and this is despite the fact that I am validating against the initializing error, analysis, so there's no initial error. But obviously, the forecast is responding to basically uncertainty in the initial conditions and possibly even errors in the initial conditions. Now I could also add on this mean integrated ice edge error. As you can see, the dotted line there is mildly above the deterministic skill measure, but as I said, that actually that mean ensemble mean integrated ice edge error is basically inflated by the spread. And so, as I said, your spread plus your spatial probability score basically adds up to your integrated ice edge error. Again, if I add, so two things about that. My spread is well below my spatial probability score. Ultimately, if I have a well-behaved ensemble system, I would really expect that the spatial probability score and the ensemble spread should be about equal. And obviously, clearly, it's under-dispersive right now. But also, if I have a good ensemble system, or if I have a good ensemble system, my spread should also be representative of my of the uncertainty in my initial conditions, which even at 10 days here is clearly not so. It's very much underrepresenting the initial condition uncertainty. And so finally, though, if I did actually want to do a comparison between the ensemble system and the deterministic systems, what I might be able to want to do in that case is look at the integrated ice edge error of the ensemble medium ice concentration. And if I do that, I get this red dotted dashed line in red there that is just mildly below the deterministic predictions. And so again, the ensemble system does kind of, even in a deterministic way, kind of improve on the forecast scores. And we can see that even better in terms of the lead time error, where again, you can see that the deterministic scores, and even and in both for the GDPS system and for the control member of our ensemble system, those are very much the ensemble medium integrated ice edge error improves on that, and of course the spatial probability score in terms of probabilistic predictions increases even more on that. And for September at least, all those predictions are beating persistence. But what I really want to talk about in this slide is the fact that again, my spread starts at 0 because there's no initial perturbations to the sea ice or ocean. And obviously, the black line there is again a representation of what the initialized uncertainty is. It's probably too big because it's really a comparison of two systems, and really you should be looking at it in terms of many different analysis systems. But it's still obviously clearly too, the initial spread is too small. If you look at the growth of error with time, you see that there's very quick growth of the sea ice error in the first 2 days as it responds to this uncertainty in the initial conditions. But after that, as you basically, once you respond to that, then the growth in spread and the growth in error are about equal in terms of the integral or the derivative of that. So if you can imagine raising the spread up to basically where the extrapolation of the skill score is there, to about halfway up to the black line there. So if we did have some value for the initial analysis in the spread, 1 minute, yes, then we'd probably have a much better prediction. And so lastly, oops, I didn't want to go that far. So the last thing I want to say is look at the spatial this as well. And in 1 minute, all I'm going to say is obviously the error is too big, the spread's too small, but at least it's in the same spot. So basically, we're getting spread where we want it to be. It'd be nice if it was bigger. So that's about it. I encourage you to look at my paper in QJRMS. Instead of talking about the summary, though, I'll basically say that what is wrong. So basically, what we have is a system. It's the ensemble system is giving us some good probabilistic skills, but we do not really represent the initial error in that ensemble. And so really what we need is an ensemble of initial conditions.
So we have time for one quick question.
I hope I understood everything.
Yeah.
You probably need an ensemble of initial conditions, but if your analyses mean states differ so much, as you seem to be showing, then it doesn't necessarily matter, no? Because you have such big biases in your analyses. Adding spread to that on a wrong analysis would not add skill, would it?
Well, that's the question, whether or not it's really biases in the initial conditions or if it's uncertainty in the initial conditions. I agree, if it is really bias in the initial conditions, then we got a problem. But if it's...
And spread is not going to, adding spread to that is not going to help you, you know, that's the point.
But if it really is uncertainty, then